Hello students, welcome back. So if you remember, we were doing ionization potential, and in the last video, if you have noticed and if you have watched, we have discussed about over there regarding ionization potential, a very important parameter of the periodic table regarding how the ionization of an atom will happen, how much energy is required, what will happen if we go along the period down the group, or rather from along the period means it can be from left to right or it can be from right to left. All these sequences we have analyzed, we have discussed, and how the energy varies, what's the effect of size, atomic size over this ionization potential, was the effect of atomic radius, rather, in terms of if we are not considering this in straightforward size and atomic radius over there, what's the effect of nuclear charge, how the electronic distribution are affected, rather it's affecting ionization potential. So all these things we have discussed, and if you and let me give you a very important thing, that is, these basics, rather, if you can notice that the nuclear charge, atomic radius, or the electronic distribution, all these things are basically the primary and the base of all the explanations. So whatever the things you will rather experience, whatever the trends or the variabilities of a particular parameter will take place within a periodic table, over there, one thing is, of course, you will check it out that there is a constant, or rather, the analysis has been done in terms of either nuclear charge variability related to that one with atomic size and nuclear pull. So all these things are being coupled together to analyze the properties of the periodic table, the various parameters of the periodic table. So today, if we have discussed many things, or rather, if we have analyzed those things about regarding ionization potential, so today we are going to discuss another very beautiful and important parameter, very important parameter regarding that is electron affinity. So today our topic of discussion is electron affinity. All right, topic of discussion is electron affinity. Now, this electron affinity, the first, of course, when I always say that we need to go by the term itself. So obviously the question will arise as a simple, very logical question. What is electron affinity? Right? We have come across once again a very new term, a new parameter, that is electron affinity. Then definitely the first question will come up. What is electron affinity? We need to understand that one first. And if we are able to understand that one, then I don't think there will be much more problem complexities and understanding the rest, or rather, not only understanding in order to analyze. That's how what's the significance, or how the electron affinity will vary throughout the table, right? So let's move on to that particular point. That is, what is this? Electron affinity is defined as the amount of energy released by an atom when an electron gets added to the valence shell of a neutral gaseous atom and converts itself into a negatively charged gaseous ion. I don't think there is very difficulty in understanding this particular sentence. It's basically in simple words, that means when an electron is getting added into the valence shell, we all know that what valence shell is, into the valence shell of a neutral gaseous atom. So we all know that all atoms are neutral. But the condition is there is a thing which has been mentioned, a neutral gaseous atom, and convert itself into a negatively charged gaseous ion. That means it's getting converted into a negatively charged species. That means, what does that signify? Signify is it is forming anions. Don't you think so? It is forming anions, right? And it means with addition, we all know that if it is an atom, it's a neutral, and with an excess of electrons. So if electrons are excess with respect to the number of protons present in a neutral atom. So with respect to the number of protons, if the new electrons are excess, then the entire atom will convert itself, will turn into an anion, into a negatively charged species. And if the ratio of number of protons and the number of electrons are not the same, and where the protons dominate and the number of protons are actually in greater, in more number, compared to the number of electrons, then it will lead to the formation of cations. So while doing this, when an electron is getting added into the valence shell, and we also know that electrons are always get rather this exchange or the transfer of electrons or the exchange of electrons or sharing, all these things always takes place with the valence electrons because they are the outside. They're present at the outside, and they're present at the boundaries. So we are really much familiar and aware that valence shell electrons, that rather also called as the valence electrons, they are actually responsible for all the chemical reactions and all the whatever the exchanges, the sharing, the donation, whatever will take place, everything will happen with respect to the valence electrons. So wherever, if electrons are leaving, that will also take place from the valence shell. If electrons are being added up, that will also take place with the valence shell, right? So what exactly then? You must be rather a bit slightly confused at energy. That how that exactly goes on with the atom. Okay, let's take a clear demonstration. This is basically chlorine atom. As you can see, the symbol is given over there, chlorine atom. This chlorine atom is basically having valence electrons, and you can see three orbits are there that you can also consider. So three orbits, they are also having valence electrons, no problem. And how many valence electrons they are having? 7. Okay. So whatever the situation is, they were having valence electrons. Now, this is a neutral atom. We all know that chlorine, it's in a normal sense, in a normal state, it's a neutral atom. No confusion in that. Now, what I'm going to do is I'm going to add an electron. There is an electron availability outside, and there is a cloud of electron present. There is somewhere, some situation. Let's consider that one. But what's the source of the electron? We're not interested right now. The point is, there are electrons are available. So chlorine is present in a similar situation, in an environment where it's surrounded by electrons. All right. So what chlorine is going to do? Chlorine is getting added, or rather, what chlorine is going to do apart from that, what electron is going to do? Electron is then definitely going to get added up. This electron is getting attached to the valence shell. This electron is getting attached to the valence shell. It's trying to penetrate inside the atom. It is trying to penetrate inside the atom. This electron is trying to penetrate inside the atom. All right. Then what's the result? If it is trying to penetrate inside the atom, what's the outcome? What's the result of this one? All right. This is leading to the formation of this anion. Okay. So this particular thing is leading to the formation of anions. Okay, is leading to the formation of anions, as you can see. So the eighth electron, so that this particular electron is trying to penetrate inside an atom of chlorine, and is finally achieved to do so. And what's the outcome? The outcome is it has converted chlorine into a negatively charged species. So with an addition of electron, it has one electron has got rather but added up. And what's the outcome? The outcome is it's converted chlorine into a negatively charged species. Okay? And along with that, what happened? Along with that, we can see there is some energy. This EA stands for This EA is basically the energy which is getting liberated. This is basically getting liberated. Okay. So with this particular, an electron is getting added up. This electron is getting added up, and what we are getting? We are getting this electron, this energy rather as a product. Apart from this particular ion, we are getting this energy as a product. Okay. So if we compare in a more simpler in a very more simpler way, then this is basically having a configuration. This is basically having a configuration of 287. This is a configuration of chlorine. And from this 287, with the addition of this electron, it has converted itself into a configuration of 288. So as you can see, so there is an addition of electron in the valence shell. There is an addition of electron in the valence shell. So from 287, so chlorine has converted itself into 288. And what's the result? The result is, as you can see, where there is energy is released. Over there, as you can see, energy is released. And this release of energy, this outcome, as a product, as you can see over here, it's EA is written over here. It's EA stands for electron affinity. And as in the definition in previous, rather in the slide, you can see you have seen that EA stands for electron, or not only EA stands for, there is a product that when the electron is getting added up, it is basically forming, and electron is getting added up. It's basically leading to the liberation of energy, and that liberation of energy is actually what we consider as the electron affinity. Now there is something which we need to understand along with this. It's the word affinity. This affinity means attraction. This word affinity means attraction. So electron affinity means electron attraction. So those will attract, rather this penetration, this inserting this electron into the valence shell, it will take place for those who loves electrons very beautifully. So converting anything into positive is basically rather leading to addition of energy, and to convert anything into negative ion, it's basically leading to rather liberation of energy. So if you compare, if you can you find any similarity, or rather any trend, any patterns between electron affinity and ionization potential? Can you find anything? Yes, of course. They are basically opposites. They're basically opposites. If you just check it out in this way, look the matter like this way: that ionization potential you are converting. That means you are providing energy, and simultaneously it is getting providing that energy that is getting simultaneously converted into a positive charge along with the liberation of electrons. So over there we need to give energy, and what we are getting? One ion and electron. Over here we again consider a neutral atom, but over with the neutral atom we are not giving energy now, we are giving electrons. So what electron we got in the ionization potential as a product, it's the same electron we are using that one in the neutrals, for neutral atoms, for converting that one into another ion. So with the addition of electron, what happens is over there by providing energy, the electrons are out. Now we are giving electrons, so obviously the energy is out. So that's a very beautiful, or rather, it's a pattern on a trend with our relationship, which electron affinity and ionization potential shares. So if you check it out, the ionization potential, it's basically if you a neutral gaseous atom. It's a basic equation. If you just make it out, it's a basic equation that neutral gaseous atom. So it's a neutral gaseous atom plus, along with that, ionization potential regarding that neutral gaseous atom plus what we are giving, we're providing energy. We are that relationship that we are providing, that neutral gaseous atom plus ionization potential. That means we're providing energy. And what the product is, we're basically getting a particular atom. So we are getting a particular a cation. We are getting a cation. We are getting a cation, and we are getting, that means, a positively charged species. So we are getting a positively charged species plus. Plus what happened? We are getting one electron. So we are getting one electron. So positively charged species and electron. So these are the products, these two other products. Now just slightly alter. Just transform, just change over the particular electron, bring back that one into the left hand side of the equation, and shift your energy, that means ionization potential, to the right. Then what will happen? The positively charged species will no longer be positive, it will convert itself into a negatively charged species. And the energy, the ionization potential which we're considering, which we're providing that one, the ionization potential has changed or converted itself into electron affinity. So this sort of relationship exists between ionization potential and electron affinity. All right. So with this, I hope that this what electron affinity is rather has become clear to all of you. This electron affinity is also known by the name electron gain enthalpy, or it's sometimes also written as electron enthalpy. So electron gain enthalpy, electron affinity, all are the same thing. Okay. Now we will switch over to, or rather move towards analysis. Electron affinity analysis. And the same thing, two ways, group-wise and period-wise. So in the group-wise, we are having down the group or up the group. So group-wise, we are having down the group or up the group. And period-wise, we will be having along the period, left to right, or along the period, right to left, two ways. So group-wise, we are having down the group or up the group. And period-wise, we are having along the period, that means from left to right or right to left. Once again, if you just check it out, these are basically the horizontal boxes with the orange. The horizontal orange boxes are basically the rows, and the vertical green boxes are the columns or the groups. Okay, so they are the green boxes are the groups, and the horizontal orange boxes are the rows. So it's not that only two, or rather only those two are the rows. It's not like it's that's basically the highlighting that one. So which are the rows and which are the groups. So based on this, we are going to start our analysis. The first definite comments, what happens down the group? What happens down the group? Firstly, what happens is, when we move down the group, atomic number increases. And if atomic number increases, we know that the nuclear charge will also increase. And if the nuclear charge increases, two things happen simultaneously down the group. The two things are, number one, the nuclear charge increases, and parallelly, the number of orbitals increases. Down the group, nuclear charge increases, and parallelly and simultaneously also, and in a similar way, the same way, the number of orbitals increase. There are two increase which take place. There is two parameters which are increasing. So the one is the nuclear charge. The second is the number of orbits. What happens next? So with the increase in the nuclear charge and the number of orbits, the atomic radius increases. So there is you can check out, you can rather think about it, and I've discussed that one in the previous ionization potential also, that nuclear charge increases. Does it reflect that the atomic radius will also increase? No. With the increase in the nuclear charge, it's not 100. We are not 100% sure that atomic radius will also increase, but we are 100% sure that if the number of orbits increases, with an increase in the nuclear charge, if the number of orbits increases, then definitely the atomic radius will increase. Okay, so with an increase in the nuclear charge, the number of orbits increases, and hence atomic radius increases. Number of orbits increase. With this, that means, what does atomic radius increase signify? Signify that distance between the nucleus and valence electrons also increases. So we know that atomic radius is actually measured till the valence shell. So actually, that means the valence electrons were there. And so that it's a distance between the nucleus and the valence electrons also increases. The distance between the nucleus and the valence electrons also increases. So now, if the distance between the nucleus and the valence electrons increases, then the effective nuclear pull over the new valence electrons will decrease. If the distance between, because they're going far away, and when they're going far away, then definitely it's normal. And we also know that if things which are far away from us, we cannot hold it much strongly, we cannot hold it much tightly. So things which are far away from us, the pull, the attraction, it decreases. It cannot be exactly similar for with those who are very closer to us, who are very closer to other things. So distance always matters when it's a relationship about the attraction. Okay. So distance is more, attraction goes down. If the distance is less, attraction increases. So it's just in inverse relationship. And what's the effect of this? That less energy released when an electron gets added to the valence shell. You may think about it. That you would think like, oh, or rather, how that is possible. Why less energy will be released? Why less energy will be released if we are adding, rather, if we are an electron is getting added into the valence shell with an increase in the number of orbits? I'll definitely come to that question, but what's the conclusion of this? The conclusion is the electron affinity decreases. So down the group of any group, down the group, electron affinity decreases. Now coming to the question. There was just a few couple of minutes back, I explained regarding how, or rather, what's the relationship between ionization potential and between electron affinity. And the equation over there, I showed that basically that same energy is getting converted. If you just check it out, that electron, if you just check it out with this value, electron is getting added, and the same energy is changing its form from uh, ionization potential to electron affinity. So firstly, it was basically getting added up into the neutral atom, but now it's getting released from the same neutral atom. Will that be will there be any difference? Because it's basically if 50, or suppose for example 50 joules of energy required to remove an electron to the valence shell, then more energy will be required, or rather a huge amount of energy will be required to add an electron to the valence shell. It basically remains the same. And if you follow that equation, I've told you can prepare that equation. You can just verify that if small amount of energy is required to remove an electron, the small amount of energy will be required to add an electron. Okay, so with that particular mathematical equation, you can just verify that numerically they will be almost the same. And if not the same, suppose they're exactly not cannot be the same because there are some other parameters which are there in effect, but at least they will not be very high. They will not be very high. So maybe it's possible that numerically even again you may not get exactly the same thing, same or value of ionization potential and the electron affinity. But this difference is basically due to some of those other parameters and other forces which are acting over there. And due to that, the difference, the values or other numerical integer values may get slightly changed. So with this, we can conclude that with electron affinity, down the group decreases. So following the same pattern, we are going to analyze, or rather, before analyzing, obviously, we're going to validate this. The validation, you're having this group over here, and there it goes, atomic number increases, as you can see. And nuclear charge increases, and number of orbits increases. With the number of orbits, nuclear charge increases, +3, +11, +19. And down the group, it's basically, we know that nuclear charge is basically nothing but related to the number of protons. And if the atomic number increases, the number of protons will also increase. And with the increase in the number of protons, the nuclear charge, that means the positive charge within the nucleus, increases. So the nuclear charge increases. So atomic radius increases. Atomic radius increases. We can confirm that one by this number, the valence shell. So the number of shells is increasing. So in the number of shells or the orbits are increasing, and definitely the atomic radius will increase. And with increase in atomic radius, the distance between the valence electrons increases. Distance between the valence electrons with whom? With the nucleus. With the nuclear, the proton, between the nucleus and the valence electrons increases. And if it increases, then definitely, if it increases, the valence shell, the valence electrons are present, as you can see, the number of orbits. So it's going away. It's going away, and with that, the effective nuclear pull of the electrons decreases. And since it decreases, less energy is released when an electron gets added to the valence shell. Less energy is released when an electron is getting added to the valence shell. And thus, electron affinity decreases. So if we have understood this one, then definitely we can obviously, if we reverse the same, there shouldn't be, I don't think there can be any confusion. What's a reverse? That means we just now discussed about the down the group, so we are not going to go with the up the group. Similarly, now the reverse, the first it was atomic number increases, so when your atomic number decreases, up the group. So if atomic number decreases, then now nuclear charge decreases, the number of orbits also decreases. And if the number of orbits decreases, then the atomic radius also decreases. And if atomic radius decreases, then the distance between the valence electrons also decreases. And if the distance between the valence electrons decreases, that means that between the nucleus and the valence electrons decreases, then the effective nuclear pull over the electrons decreases. And if the effective nuclear pull over the electrons decreases, then more energy is released when an electron is added to the valence shell. More energy is released if effective nuclear pull increases. If that is so, then more energy is released when an electron is getting added to the valence shell. Now here lies the small question, that why it is so? The same thing. If more energy is required to remove an electron, then more energy is required to add an electron to the valence shell. Obviously, more energy will be required. Okay, because less space over there. So we need to open up the space, and then we are just adding up that one by great force. We're creating space over there, so more energy is required, and hence electron affinity increases up the group. What about the trend along the period? All right, before going that, we are having the validation, of course. So we are having the validation. So the validation of the same thing, atomic number decreases. It's having over there, we're going to check it out. That's Z equals to atomic number decreases, 85, 87, 55, 37. So it goes on decreasing numbers. Nuclear charge decreases, the number of orbits decreases. So nuclear charge plus 19, 11, 3. So the atomic radius decreases, that's orbits 19, 11, 3. As you can see, that orbits are decreasing, KLMN. So 4 orbits are over here, 3 orbits over here, 2 orbits. So number of orbits are decreasing, and with the decrease in the number of orbits, definitely the atomic radius will decrease. And if the atomic radius decreases, then the distance between the valence electrons will decrease. And if the distance between the valence electrons and the nucleus decreases, then the effective nuclear pull increases. If the effective nuclear pull of the electrons increases, then more energy is released when an electron is added to the valence shell. More energy is released when an electron is added from the valence shell. There is a word missing over there. It's a word added has to be there. Added has to be added over there. The word added has to be added over there. So more energy is released when an electron is added to the valence shell. And thus, electron affinity increases. As simple as that. Okay. So move on to the period now. We're having the period from left to right. From left to right, we're having atomic number increases. Exactly the similar way. Atomic number increases. Nuclear charge increases, there is a slight change. That's number of orbits remain the same. Number of orbits remains the same. Previously, the number of orbits, or rather for the group wise, for the groups, the number of orbits were basically increasing. But over here, the number of orbits remains the same. And if the number of orbits remains the same, with the increase in the nuclear charge, the effective nuclear pull of the valence electrons increases. And if the effective nuclear pull of the valence electron is increasing, then the atomic radius decreases. And if the atomic radius decreases, then distance between the nucleus and valence electrons also decreases. And if the distance between the nucleus and valence electrons decreases, then more energy is released when an electron is added to the valence shell, because effective nuclear pull increases, so less space, so more energy is required to increase the space and to add an electron over there, overcoming everything. So more energy is released, more work has to be done, and thus electron affinity increases along the period from left to right. So let's do the validation. We are having the period over the lithium, beryllium, boron, carbon, nitrogen in this period, and we can see atomic number increases. And if atomic number is increasing, the number of orbits remain the same. Number of orbits remains the same. It's 2, 1, 2, 2, 2, 3, 2, 4. So its number of orbits remains the same. And when the number of orbits remains the same, the effective nuclear pull of the valence electron increases, and that's leading to the atomic radius decrease. And if the atomic radius decreases, the distance between the nucleus and the valence electrons also decreases. And when the distance between the nucleus and valence electrons decreases, then more energy is released when an electron is added to the valence shell, because effective nuclear pull is increased over there. Strong forces are working, and thus electron affinity increases. That is, so conclusion, electron affinity increases from left to right of a period. What happens along the period from right to left? Just the opposite, we will move on. So atomic radius number decreases, and that means nuclear charge decreases, that with leading to the number of orbits remain the same. The only variable, the nuclear charge decreases. So if the nuclear charge decreases, effective nuclear pull over the valence electrons decreases. If the effective nuclear pull over the valence electrons decreases, then atomic radius increases. If the atomic radius increases, then distance between the nucleus and valence electrons also increases. If the distance between the valence electrons and the nucleus increases, then less energy is released when an electron is added to the valence shell. And if less energy is released, the conclusion is electron affinity decreases. That's the conclusion. Validation over there, you are having atomic number decreases. If atomic number decreases, then nuclear charge decreases. Number of orbits remain the same. If number of orbits remains the same, then the effective nuclear pull over the valence electrons decreases. If the effective nuclear pull over the valence electrons decreases, then the atomic radius decreases. If the atomic radius decreases, the distance between the nucleus and the valence electrons also increases. If the distance between the nucleus and valence electrons increases, then less energy is released when an electron is added to the valence shell, and thus electron affinity decreases. So the conclusion from here we can draw that electron affinity is minimum for the alkali metals. So electron affinity is minimum for alkali metals. We haven't considered over here the transition metals. So there are other elements, but in a general, what you are having with if we compare what you're having that's based on the syllabus right now, what you're based on your syllabus. So electron affinity is minimum for alkali metal based on your syllabus. That means for class 9. So for class 9 electron affinity, we are not considering over here the transition elements. So they're having the scenario can get slightly changed, but over here based on this particular thing, that electron affinity is minimum for the alkali metals, which have a single electron outside a closed shell, and it generally increases across a period from left to right of the table, with halogens having maximum. So there is an exception over here, as you can see, there is an exception with halogens maximum. It's an exceptional trend. The trend is down the group. We know that down the group, the electron affinity decreases. Down the group, electron affinity decreases. But there is a slight exceptional scenario. The exception is chlorine, which comes after fluorine, is having a greater electron affinity compared to fluorine. But as per the theory, as per the expectation, it shouldn't be. Fluorine should have, or rather, should have the highest electron affinity, but that's not the reality. The reality is electron affinity of chlorine is greater than that of fluorine. So the trend down the group is chlorine greater than fluorine, greater than bromine, and greater than iodine. So that's the trend, and there how it goes. That chlorine is having the highest electron affinity compared to, rather, from fluorine and within the group, and hence fluoride comes after fluorine and followed by Br, and then the pattern remains, the expectation that the trend remains the same. So I hope I have been able to demonstrate this electron affinity in a very rather clear way, in a very simple way, and if all of you have able to understand this electron affinity. But still, if there is any doubt or any confusion, anyone with any confusion, you're free to ask questions. Contact me over here. The details are there, and till then, I'll put up, rather, I'll stop over here for today's lecture. We'll catch you up with another topic, any other interesting topics related to chemistry and periodic table in the upcoming classes. Till then, stay safe and take a very good care of yourself. Thank you.